So again, guys, in this section now, 5-6, we're going to learn about more shortcuts. Now today, though, these are the last shortcuts that we're going to be using to prove two triangles are congruent. So once again, remember that the long way to prove that two triangles are congruent is to prove that you have three sides that are corresponding and congruent to the other triangle, and you have three angles that are corresponding and congruent. And so you need to prove a lot of things to be able to prove. You need to know all three sides of both triangles and all three angles of both triangles, and you don't always have that luxury to do that. And so shortcuts are very helpful. The first shortcut you learned was side angle side. So it was two sides and the included angle, okay? And so you learned that. The second one that you learned was side, 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 and it was the three sides. Even this one is just half of the long way. It's this part of it, you know? The third method specifically, well, actually, I'm going to go to 5, is the HL theorem. And the HL theorem is a hypotenuse. Oh, I'm spelling this wrong. Hypotenuse and a leg. Now, the hypotenuse leg, only a right triangle has a hypotenuse. And so this is for right triangles only, and it's why I listed at the end. And then today you're going to learn the missing two that we hadn't covered before, and it's ASA and AAS. ASA is two angles and the included side, and AAS is two angles again, and it's the non-included side. Now, the non-included side, it does matter which side, so again, I'm going to star it, but we'll talk about it today. But basically, these are the 5 shortcuts where you don't have to prove every angle and every side. So the first one is ASA congruence theorem. Again, this is if two angles and the included side of one triangle are congruent to two angles and the included side of a second triangle, then the two triangles are congruent. So if you look at the picture, it makes it pretty clear what they're talking about. The two angles that we're referring to is angle A matches with angle D, angle C matches with angle F. So you have two angles in the one triangle that are corresponding and congruent to two angles in the other. The included side means that the side or the segment in between those two angles is congruent to the other one. So it's not this side or this side. It has to be the included side. So if you have, again, two angles and the included side of one matching with two angles and the included side of another, then the triangles are congruent using angle side angle theorem. Now here we get to the angle side congruence theorem. And this says that if two angles and a non-included side of one triangle are congruent to two angles and the corresponding non-included side of a second triangle, then the triangles are congruent. And so this part about corresponding matters, okay? So let's talk about what we mean. First of all, two angles, that's easy, right? We're going to identify two angles here that are similar. We've got angle G matches, or not similar, but congruent. Angle G is congruent with angle K. Angle J is congruent with angle M. Notice the included side is down here, and we know nothing about the included side, right? So this isn't angle side angle because that included side is, we're not told that it's equal. What we have is this other side over here. Okay, so that's the side opposite the single tick mark. If that side on the other triangle is congruent, then angle side works here. So notice where the single tick mark is, and notice that it's opposite the single angle. Again, the single congruence mark. That means that angle side is what works here. It's two angles and the corresponding non-included side. So you might say, well, what's the non-corresponding side? That's not like the non-corresponding, non-included side. That's kind of weird, right? Well, look over here. If the tick mark was here, that would be a problem, because notice that this side is opposite the double tick mark. So it's not the correct corresponding part. So it has to be opposite the same kind of angle, the single tick mark. We'll do a lot of examples, but that's what that means. So here we summarize all of it. And again, you want to make sure that you can visualize this when you're thinking about it. When I say side, 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 an image of two triangles where all three sides are corresponding and congruent. And again, the definition, okay? The second one, side, angle, side. Again, you want to be able to recognize that it means the side, the other side, and the included angle, okay? And again, be able to identify it or visualize it, okay? When I go to the third one, you want to be able to think HL. First of all, you need to be thinking of a right triangle. You're going to need the hypotenuse in both cases, and you're going to need one of the other two legs. If you have that, then you have the HL theorem. When I go to angle, side, angle, again, you want to know what that looks like. You have an angle, another angle, and the included side. Angle, angle, included side. And understand and know what that means to you. And the last one is angle, angle, side. So you've got angle, angle, and this, let's say, side opposite the single tick mark. Here you have angle, angle, and the side opposite the single tick mark. So it's a corresponding non-included side. And if you can kind of visualize these things, guys, I'm telling you, it's going to make this work a little bit easier for you. So we're ready to do proofs. Now this is the hardest proof on the page, so I'm going to come back to this one after I do everything else. So you might want to skip ahead and come back to this video after we've done the other ones. So I sort of skipped this one and went on, but the last proof was just as difficult as this one, and it's the same skill. So anyway, we're going to do it together. We're going to start out by doing our statements, and then we're going to go to our reasons, and we're going to start our proof here. Our step one, again, angle X is congruent to angle V, and that's given. And I'm going to go to my picture and I'm going to identify it. So angle X here is congruent to angle V over here. My second list here, number 2, is that angle YZW is congruent to angle YWZ. And again, I'm going to come over to here and figure that out. YZW is here, and it's equal to YWZ. And so notice that I've got now 2 equal angles that they've given me. Now from here, before I do anything else, I do want you to notice that you now have in this center triangle right here, what you have is 2 angles that are the same. So this is going to be an isosceles triangle. And remember that if the base angles are the same, the sides opposite those angles are also congruent. And so I can say in my proof now, this is my first part that I'm doing on my own here, I'm going to say that YZ is congruent to YW. And the reason that those 2 sides are congruent is because of the converse of the base angles theorem. So if you remember, the base angles theorem says that if 2 sides are equal, the base angles are equal. And the converse says if the base angles are equal, then the sides are equal or congruent. So now I have a side that I was able to prove. The next thing I know is I have to kind of think about this. Let me see what else they gave me here, right? Number 4, they also gave me that XY is congruent to VY. Now again, this was a given. So let me see, what does that mean in this big picture here, right? So let me come over here. XY over here is congruent to YV. And so notice what I've got here. I've got 2 sides. I don't have the included angle. I don't have 3 sides. And right now, they want me to prove, because what they're really wanting me to prove, and I should have mentioned this at the beginning, is that these 2 yellow triangles are congruent. Well, I'm going to need to know another angle. And I'm going to need to know how to do that, right? Figure that out. Well, we just did that in the very last slide because we discussed that and we said, well, wait a second. These angles here form a linear pair. So I've got to do all the proving again to show that these two angles here must be congruent. And when I do, right, I'm going to have angle, angle, and a side. And so this is going to be AAS once I'm able to prove that those two angles are congruent, that the blue angles are congruent. So how do I do that? Well, I start that whole process again that I did before. Notice that the blue and the red angle here form a linear pair. So I'm going to say that angle XZY and angle YZW are a linear pair. Okay? And I'm also going to include the other one on the other side. So I'm going to do angle VWY and angle YWZ. They're also a linear pair. And I know that both of those are linear pairs because I know the definition of a linear pair. I know what they look like. So that's what that is. When I go to 6, I'm going to say that these two sets of angles are supplementary. So angle VWY and angle YWZ, I know that these are supplementary. And the reason I know they're supplementary is because the linear pair postulate says they are. So again, remember I told you these are like patterns, they flow. The next thing I'm going to do is I'm going to say that angle XZY plus angle YZW and angle VWY plus angle YWZ both equal 180 degrees. And I know that because that's definition of supplementary angles. That tells me their sum is 180. So like I mentioned in the last example in this slideshow and now here, again, whenever I'm trying to prove that angles that make up a linear pair are congruent, or something to that effect, I'm going to have to follow the same pattern pretty much every time. I'm going to have to first identify the linear pair or pairs, then I'm going to have to say that the linear pairs are supplementary, and then I'm going to have to make them add up and equal 180. And again, it's going to be the same 3 reasons in that order. So again, now that I was able to set up the supplementary part, now I have to kind of address how I know that they're equal, okay? And so this is, again, going to require a very structured order to, what you're doing here. So let me kind of change colors. So let me go to number 8. Basically now what I'm going to do is I'm going to take those two equations that equaled 180, and I'm going to make the two equations equal themselves. So I'm going to, equal each other. So instead of both of them equaling 180, I'm going to say that angle XZY plus angle YZW equals angle VWY plus YWZ. And that reason, okay, is going to be substitution. So I'm just substituting one of them in for 180 degrees. Now, again, I'm going to do substitution again, because remember, what I want to get down to is that XZY, I want to get down to the fact that this equals, this angle in blue here equals the other triple blue striped, which is YWV or VWY. Okay, YWV or VWY. It's this one. I want to get to the point of saying that those two angles equal each other. And so notice that one is on this side of the equal sign and one is on the other. So I've got to find a way of getting rid of YZW and YWZ. Well, notice up here I said that YZW and YWZ were equal. So I could also substitute there. So what I'm going to do is I'm going to substitute in here again. I'm going to keep the first one, which I know I want in my final, oh my gosh, why do I keep writing it wrong? XZY, okay? And then instead of YZW, I'm going to substitute it for YWZ, which I know is the same thing. Now you might say, well, why do you want it to say the same thing? Well, I'm going to show you now. An angle YWZ. So the only thing I changed from here to here is I just substituted YWZ for YZW. And again, I know that I can because I've already told you up here in the proof that they're equal or congruent. They were actually given to me as being congruent. So again, this is a substitution. Again, substitution. And then now, because I have the same thing on both sides, I know that I can just be left with XZY equals angle VWY. And you might say, well, what did I do? Well, guess what? I subtracted YWZ from both sides. Notice I just basically subtracted them out. So it's like canceling, okay? And so this is the subtraction property of equality that I did that. That's why I wanted to get to that point, so that I could subtract it out, and therefore it left me with the two angles that I wanted to prove were equal from the very beginning. The angles that I'm talking about here is this angle here and this angle here. I basically just proved through all these steps, and it took a while, but it really took this entire process to prove that those two angles were equal. So I know that's a little bit complex, but again, now that I know those angles are equal, now I look at my yellow triangles and I'm like, okay, I've got an angle, and I have the side opposite the blue angle. So angle, angle, and the corresponding non-included side opposite from that blue angle. So again, now I'm ready to say that my triangles are congruent. So I'm going to come here to this final statement. And I know that they're congruent because, again, angle, angle, side theorem is what I used. So it's very repetitive once you do these enough times when you're dealing with these linear pairs and things like that. You might want to try walking yourself through it. Make sure you understand what we're doing. The last one is the same. Really check that. Try to see if you can follow the process. And the more you practice it, the easier it's going to become for you. So in example 2 here, we want to prove that these two triangles are congruent. So we want to prove that this yellow triangle at the top is congruent to this purple triangle down here at the bottom. So let's start with our basic two-column proof. Statements and reasons. And I'm going to start with the given. And I'm going to start with one given at a time. So the first given is that segment JL bisects angle KLM. And I know that that's given. So for me, I'm going to go and I'm going to look for that segment. And I see that that segment is right here, JL. And when they tell me that it bisects angle KLM, KLM is this large angle there. Okay, and so if I know that it bisects it, what I then know is that this angle piece right here, this little blue angle, is going to be congruent to this angle. And the reason I know that, let me write it, angle KLM is going to be congruent to angle MLJ. And the reason I know that is because I know what an angle bisector is. Definition of angle bisector. I know that if I have an angle bisector, my large angle has now been cut into two equal parts. So that's the definition. So that's what flowed from this given. Then I go to the next given. I don't have to do my givens in a row. Angle K is congruent to angle M. So again, that's a given. Now I come over to my picture and I see, okay, angle K is here and angle M is here. So right now I see that I have two matching angles, okay, one in each triangle. Let me kind of erase now all of this and clean it up a little bit. Basically, I know this angle equals this angle equals this one. So I have angle, angle. I'm not going to be able to figure out this third angle. I don't have enough. I mean, I kind of do have enough. I know that there's a third angles theorem that says if two angles of one triangle are congruent to two angles of another, the third angles are congruent. So I actually do have enough to know that this angle here equals this one. The problem is that I don't have a shortcut for three angles. And so it's not going to help me anyway. So I'm not going to add it to my proof, and I'm not even going to put it there. What I do know is when I have two angles, the ones that I have is angle side angle and angle angle side. So angle side angle would mean that KL is equal or congruent to LM. And again, I don't have enough information for that. The one that I do know for sure is that JL equals itself. So I know that this side is equal to itself. And so now I'm able to go to my proof and do JL is congruent to LJ. And I know that the line equals itself because of the reflexive property. So reflexive property of congruence. And so now notice what I've got going on here. I've got an angle, and a side opposite the single congruence angle. And then here, angle, and a side opposite the single congruence angle. So guess what? I now have what I need to prove what they wanted. They wanted me to prove that triangle JKL was congruent to triangle JML, and I did using angle, side. And notice in my proof, I listed the one angle. I listed, I should have another angle somewhere. Angle K is congruent to angle M. There's my second angle, and here is my non-included corresponding side. And so I have my A, and my S here, which is my proof. Okay, my reason for my proof. When I come to these problems here, I'm going to just kind of use the skills I have. It wants to know what postulates prove that the triangles are congruent. Notice if this is 15 and this is 15, they're equal. If this is 150 and this is 150, they're equal. And if you notice, what you've got going on here is angle, side, angle. And on this one, you have angle, side, angle. And so you have angle, side, angle is the reason you can prove that this is fine. Okay? When you go to your second triangle, you have a right angle. Notice you have the hypotenuses are the same and a leg is the same. And so you know these triangles are congruent because of hypotenuse leg. Now, is hypotenuse leg the only one you can use here? Absolutely not. It's definitely one. The other one I can use is I know this line equals itself. So I know the reflexive property works here. And if that line equals itself, then notice I have all three lines in one, match all three lines in the other. So side, side, side. And notice that I also have side, angle, side there, and side, angle, side here. So I also have SAS. So this one actually has three ways I could prove it. The fastest and easiest is the HL theorem. So if I was doing a proof, I'd pick HL. And then I go to the last one, and I start trying to figure this one out too. Notice that I know that this line equals itself. And so notice it's segment 1, segment 2, segment 3 is equal to 1, 2, and 3. So side, side, side works. Okay. Another one that works is notice that this angle here is going to be equal to this one because vertical angles are equal. This one is going to be equal to this one because vertical angles are equal. And notice then what you've got here is the side, the angle, and the side. The side, the included angle, and the side. So again, this one, we can also prove this one with side, angle, side. I can't prove it with angle, angle, side, or angle, side, angle, and I can't use HL theorem because even though this looks like it could be 90 degrees, they did not tell me that it was, and we cannot assume. So those are the two reasons why I can prove those congruent. I'm going to come and try this proof. Hopefully this one's not as bad as the one that we're going to do next. I haven't done this one yet. But here we have our statements, and here we have our reasons. So I'm going to take my time here, and I'm going to try to figure this one out. First, I'm going to start with angle FAB is congruent to angle GED. Now, I know this is given. Now I'm actually going to look at my graph and try to figure out what they're talking about there, right? So I've got FAB, that's this angle out here, is equal to GED. That's this angle out here, okay? The second part of this one, the next given, angle ABC is congruent to angle EDC. And I don't even have to put 2 on that. I can just leave it as part of 1 and it's still part of the given. So let me go and do that one. So angle ABC, that angle there, is equal to EDC, which is this angle here. So now I have those 2 angles. Then I have line segment AC is congruent to line segment EC, and that's also given. So let's figure out that one. So AC, this line right here, is congruent to EC. So I know those lines are going to be congruent. So now I've got an exterior angle, an interior angle, I have a side, so it's getting interesting. So I have to start really now analyzing which are my methods and which one can I use here. Remember, you've got side, angle, side. Well, I only have one side, so I don't think I'm going to be able to do, and I don't have a shared side. So I feel like my side, angle, side is going to be knocked out here. Side, 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 same thing. I don't have enough sides. HL, guess what? It's not a right triangle. So I've got angle, side, angle, and angle, angle, side. And right now, I need to figure out which one. To me, I think the one that I'm going to be able to prove is angle, angle, side. Because if I can prove that this angle here and this angle here are equal, then I can prove these 2 triangles are congruent using angle, angle, side. And I know that those angles are equal, and I'm going to tell you why. My first step is that angle FAB and angle FAB and angle BAC are a linear pair. Okay, and not only are those 2 a linear pair actually, but also on the other side, angle GED and angle DEC are also a linear pair. And I know these are linear pairs because I know what they look like, because I know the definition of a linear pair. So again, I'm identifying that they're a linear pair. Now I'm going to talk about what's important about them. Linear pairs are supplementary. So I know that angle FAB and angle BAC and angle GED and angle DEC are supplementary. And the reason I know that linear pairs are supplementary is because we learned in one of our chapters the linear pair postulate, which says that linear pairs are supplementary. From there, I'm going to go down to the fact that I know that angle FAB plus angle BAC equals 180 degrees, and I know that angle GED and angle DEC also equal 180 degrees. And again, this goes from the same stuff. This is definition of a supplementary angle, or of supplementary angles. So anytime I come up with, I see a linear pair, guys, these 3 things sort of flow together. First, I identify them using the definition. Then I say they're supplementary using the postulate. And then I say that they add up, their sum is 180 using the definition of supplementary angles. Okay? Now what I can do is I can rewrite this as angle FAB plus angle BAC equals angle GED plus angle DEC. So basically, I'm using substitution here. So for here, it's substitution. Okay. Now, up here somewhere, I told you guys that angle FAB, this was given, equals GED. So I can sub in at any point. I can sub in FAB or GED for each other. So I'm going to come in here and I'm going to substitute. Instead of FAB, I'm going to use GED. I'm going to say angle GED plus angle BAC equals angle GED plus angle DEC. And I can substitute that in, so substitution is the way to go here. And then notice what I can do here. Since angle GED is in both sides, I could subtract it out technically, and I can say that angle BAC is congruent or equal to angle DEC. And that would be subtraction property of equality. So because I'm subtracting that out, I now am left with BAC equaling DEC. Notice BAC equals DEC. All these steps were required for me to show that those two angles are equal to each other. So again, now when I look at my proof, notice that I proved that angle B and angle D are equal to each other. That was given. That was here. Okay. We proved that AC equaled EC. That was given. And now we proved this other angle was equal here. So now I have angle, angle, and corresponding side. So here I know that my triangle now ABC is congruent to triangle EDC, and I know that what I used to do it was AAS. Now it took a lot. I mean, basically all of this went into proving that this angle right here was equal to this angle here. And that's a lot of work for that. But again, it's kind of how you have to do it.